So let's talk about modifying or patching binaries. It's generally useful for cracking something, but it has uses beyond that. Sometimes you just want to change the behavior of a program a little bit. And for example, sometimes in CTF challenges, you want to bypass some checks just to make the exploit development easier. And then later you can go back and edit the check back in. A very long time ago, at the beginning of my channel, I created this episode called Reversing and Cracking First Simple Program. It's in the binary exploitation playlist, and it's the episode Hex 5. It's a very simple program that we are looking at. We are basically just having a very, very simple password check. And back when I made this, I decided to just dynamically show you that you can change the execution flow of a program. So back then I just used GDB and then changed what happens at the if comparison. And I didn't patch the binary because I thought that would add a bit too much complexity to that video. I just wanted to show you that you can change and debug these things. And I always thought eventually I will make a video about binary patching. Almost 4 years later, I still haven't done it. So I guess now is the time where I just show you the basics of patching a binary. So here's the code again of the license key check. It first checks that you have supplied an argument. If you didn't, it will tell you how to use it. So you have to pass in a key. If you pass in a key, it will print that it's checking this license. And then it performs a simple string compare to this hard-coded password. And then it prints access granted or wrong. So here's it compiled, and when we enter a wrong license, it's checking the ASD license and it says wrong. Obviously, it's easy to find the license key. Simply enter strings on this binary and you'll find the hard-coded key. But let's patch this binary. So let's open this in GDB and look at the disassembly. So here's the string compare. And after that, we have a test EAX. The return value from string compare is an integer. In this case, we are checking if it's 0 or not. And so it uses this test instruction on EAX. Basically, this will decide if it's was 0 or not. And this is then followed by a jump not equal. So it will either jump to 7.3a down here and execute this puts call, or it will execute this code here. So this jump not equal is obviously determining if we are jumping to the wrong case or the access granted case. So if we would invert that jump not equal and make it a jump equal, then in the cases where we supply a wrong license key, it should jump to the access granted. So if we look at the addresses here, we see that the jump not equal instruction starts at 7 to 8, and then at 7 to C is the next instruction. So this instruction is 2 bytes long. It's 7 to A and 7 to B. This is the jump not equal instruction. And then at 7 to C, we have this load immediate address. Okay, so let's look at the byte value of this. Examine 2 bytes at this address. Okay, bytes wasn't really useful. It shows it in integer. Here with X in hex format, you can see the raw hex values. So here you can also learn about a small detail of how the jump not equal instruction works. So you see that the jump destination address here is 2 bytes, but the whole instruction is only 2 bytes large. And actually, if you think about it, this is position independent code, so it could be placed anywhere in memory. So hard coding addresses inside of this jump instruction wouldn't make sense at all. That's why this is a relative jump. And so you can calculate the jump destination yourself. And the way it works is you take the address of the next instruction, and then you add the offset that is specified in this jump not equal instruction. So 7 to C plus E is 7.3a, and the jump not equal is to 7.3a. So if you want to control where it would jump to, you have to control this byte. So here I have the Intel architecture manual. So in here we can look up the jump not equal instruction. So you can see here it's hex 7.5 and then the jump destination, the byte after it. And this matches our jump not equal is 7.5. So let's look for a jump equal. Here's the jump equal, and it's 7.4. Okay, so we only need to change this byte from a 7.5 to a 7.4, and it should work. So how do we do this? Let's go a little bit of the hardcore way first, like the old school kind of way, okay? So our instruction is at 7 to A, and because we have here a position independent executable, this is actually also the offset inside of the actual like binary file, so it will be easy to find. But if you're debugging this program and this program is somewhere else loaded in memory and the address is much larger, you always need to figure out what is the base address. Where is this binary loaded into memory? And then you need to subtract that base address because you are only interested in the offset inside of the file. The second method that you can do is pattern matching. So let's actually print a couple of more instructions. So 750E 4880 and so forth. And let's just keep that in our mind. So I created a new tab so we can have the list here easily accessible. I told you we do this like old school dirty. So let's go into Vim. Okay, obviously this looks crazy because it's a binary file. So you can find in here a few printable characters. With / you can also search for stuff. Let's jump to the usage. All right, and I press I to insert mode, and then I change here something. But notice when I delete a character, everything shifts. Delete a character, everything shifts. If you do this, you need to always make sure to add the exact number of characters again. You must not move the binary around. You can't just like remove characters. This will shift everything around and everything breaks. What you can do is only modify binaries in place and change them to something. So key had 3 letters, so we can replace those 3 keys. So let's save that file, and now let's execute it. And now the usage says AAA instead of key. But we want to change the jump not equal. So we can use here a little bit of Vim magic. We can basically run this whole file through XXD, which gives us hex dump. So now we have here the hex dump output generated by XXD. And so now we want to basically find our byte pattern here. So 750E48. So let's search for the 75 by pressing escape /75. So here's a 75, but after there's a 2F, so not ours. Next one is here, F0, not ours. 7559, not our bytes. So here is a 750E, and we have a 488D. 488D. So this looks like the correct location. Okay, maybe I should have mentioned this. On the left, you can find the addresses, the offset inside of the file. In the middle, you can find the raw bytes of the file. And to the right, you can see the ASCII interpretation of these bytes. So let's change the bytes. We know 75 is the jump not equal, so let's turn this into a 74. Again, you are only allowed to change in place things, so no moving around. So we have 74. And now we reverse it. So we basically do the same command again, xxd, but with -r, because now we take the hex dump, pipe it back through xxd, and we get the binary output again. Let's save that file. Let's execute license. And now let's enter a wrong key. Access granted. Also ASD works now, which earlier didn't work. So this was a little bit the hardcore method. Obviously there are nowadays a few more tools that are a bit nicer. So let's recompile the code to recover the original one. Probably the best tool for binary patching is Binary Ninja. They make it really comfortable. Binary Ninja is more than just patching. It's a full disassembler and so forth. I've used it a lot in the Pwn Adventure series, so check that one out. But for patching here, I downloaded now the demo version. So let's start it, and we open the license file. So we are here at start. Here it finds main. So here's the main function. So you can see the checking license and then the printf. Here's the string compare, and you see before it the loading of the one string constant with the real key. And then you can see here the wrong branch and the access granted branch. And here you can see the jump not equal. Now Binary Ninja also has a very comfortable hex editor. So here in the bottom right, you can change the graph view to the hex editor. And so it's basically, just a regular hex editor. And so we can go to the 72A, and you can also see here our 750E48. But let's go back to the disassembly graph. Okay, so let's check this out. So when you hover over it, you can see the opcode 750E. But let's patch it. You can do a right click and then patch. And because it's aware that it's a jump not equal, it will offer you a couple of options. You can say always let it branch to the target address. You can invert the branch or never branch. So we could, for example, just invert the branch. And now you see that it's jump equal. And if we go into the hex editor, we see that it was changed to a 740E. Now you can save this file, license to cracked, make it executable, and let's check it out. It works, access granted. You can also use Ctrl-Z to undo. Let's check out the linear disassembly. So here's our jump not equal, and you can see that right after our jump not equal, you get the access granted. This means only when this check basically fails, it will jump to the wrong case. So another thing you could do is you could just replace this jump not equal with a knob. So you can say here never branch, which basically turns the 2 bytes into knobs instead, and now it will always run into access granted. And obviously here inside we have theoretically the other code, but it's never reached. You can also just assemble any assembly code you want. So we can click here on assemble. So we could restore this jump here. So let's jump not equal 73A. And now it did something bad. So this is where you need to be careful. So you see here, this code suddenly makes no sense. Somehow our access granted is gone. And the reason for that is here. The green value is the address, and the faint gray value here, those are the actual opcode bytes. And suddenly it's not 2 bytes anymore. It's not the small relative jump that it was before. Now it takes 1, 2, 3, 4, 5, 6 bytes for this whole instruction. But there was only space for knobs, and so it has overwritten other instructions after it and thus corrupted here completely the code after it. So this is something you need to be careful with. You always need to think about how many bytes does an instruction take, does it fit in there, and never move bytes around. You must always only in place replace them. So you always have to think about how many bytes does an instruction take, and then you must never remove them or add them. Always only replace them. Always replace the bytes. If you need to get rid of an instruction, don't just delete the opcodes, but replace them with knob 90. And if you need additional code somewhere, then it gets a bit tricky and you can't insert here a lot of code. So especially if you need more complex code, what typically people are doing is they are looking for code caves. They look for executable space inside of this binary that is not used and then use that to write something. So I'm not sure if we can find a lot in this small binary here. But for example, like this code is unused right now. So you could write here a very small relative jump that jumps back here. And then you have a couple of bytes where you can write your own code and then you can jump back. That might be an idea. Things like this could work. You know, you need to be just have some creativity and then you can figure this out. Just make sure you don't overwrite stuff you need and you don't move the bytes around. Don't shift them. Don't delete stuff or add stuff. Always only replace. Let's try patching with Ghidra. Okay, let's go to main. So here we also obviously have the nice decompilation of that. So you would see here also the string compare. The cool thing about Ghidra is also you can now click in the decompilation here at this if, and then it will take you to where this if here is evaluated. Now Ghidra disassembles this as a J and Z, jump not 0, while GDB and Binary Ninja were disassembling it as jump not equal. They have the same meaning. It doesn't really matter, okay? Like mnemonics, the way the text representation is just something for humans to understand. Important is only, you know, the raw bytes 7.5. That's actually what the CPU is interpreting. Anyway, I'm not sure if I ever patched something with Ghidra, but let's just go with the flow. I would just assume a right click. Patch instruction. This processor received a rating of gold during testing. You should rarely encounter an error, but please let us know if you do. Okay, this is fancy. It gives you here like 2 text boxes. So I guess jump 0. Cool, it has autocompletion. So let's make a jump 0 out of this. Oh, it also tells you how it will change it. 740E, I guess. Okay, let's press enter. Okay, this worked. That was a pretty good experience. Let's turn it into a knob. Enter. So now I don't want to have a knob with this as a parameter. Can I just like remove that? Yeah, it shows me different variations that I can do. So I could do like a 2-byte knob, or I could just do a plain 90s knob. So let's do that. And then obviously we have the second instruction here that we now also need to change. Patch instruction. And so let's make that, I wonder, can I type? No, okay. So let's make this also just a regular knob. There we go. And now you can see also the decompilation update. Now it's just access granted. Cool. So let's see if we can also save this. Okay, so it's license ghidra.bin. It's recognized as an executable. Segmentation fault. Okay. Okay, so I don't think this worked. GDB says it's not in executable format. I guess let's Google. Okay, so this person is also using the binary export. I mean, it does say it creates like an executable elf. Oh, it says missing section headers. It's also like interpreter lib64l. It just stops. Yeah, so this is how the normal license file looks like. They also have a different size. I don't know. So something is broken with Ghidra. If you figured it out, please write it in the comments and I will pin it, and then maybe other people can find the solution what's wrong here. But you know now how to do like hardcore patching with Vim. So you can still use Ghidra and perform the change you want. And then you can observe here the changes. And then together with the memory map, you will find the base address, which is 10000. So you subtract from this address here, the base address, and then you have the remaining 72A. So now you know the offset inside of the file, 72A, and then you can open a hex editor, and then you can do the change to the 74. So even though you can't do directly the modification with Ghidra, you can still use it to figure out what the byte values are and then go into the hex editor and change it. I guess I owe it to Radare to also show you quickly how you can patch with Radare or Radare. Always, always, always install Radare from GitHub and never use the packet manager. And I guess you can also always use master. If something breaks in master, you can always like go back to some other tag. While this is compiling, I can also show you the radare2 book. If you want to get started with Radare, I can really recommend this Radare book here. And I also can't remember anything about Radare. Every time I use it, I need to look up write-ups and tutorials and blog posts and stuff. So I guess I want to know how to write data. Radare can manipulate a loaded binary file in many ways. And there are a lot of options. Okay, it's in the W. Okay, I should be able to figure this out. So let's install Radare. Okay, so now let's open this license1 file in Radare. Very brief Radare introduction. At the left, you can see an address. That's basically the offset inside of the file. And we can also analyze it, but it's not like super important for us right now. Seek, you have also heard in the context of any kind of file manipulation. Seek is just like moving the cursor around where inside of the file you are seeking somewhere. So with seek and an address, you can seek there, and seek entry 0 will go to the defined binary entry point, but it was there already by default, I guess. So let's enter visual mode. Oh, we press space. So here's the entry function. We know here's libc start main, and here's main. So we can seek. No, this didn't work. So it knows of the symbol main, so we want to go there. Help. Nope. Question mark. Okay, so with colon, we can just type in radare command. So we can do seek to sym main. All right, so now we are in main. So here we can see the check if it shows the usage or checks the license key check. And then here we have the jump not equal. Now that was somehow a way. Okay. I love Radare, but I don't know how to use it. Okay, so here's, okay, so I pressed just V because I don't know why I pressed it, but then you get this view of functions. Isn't that cool? You can just quickly go through the functions. So this is also how we could have gotten to main. All right, I want to see addresses. P. Okay, P. Okay, so now we also get the output. We have here the address, the opcode 750E, and the and we see the disassembly. So basically, we want to seek to this address here, colon seek 72A. And I guess we want to leave visual view now. Okay, seek 0x72A. And then I guess we want to quickly, just to verify, read something. So I guess that's the wrong command. Oh, we want to print stuff. Right, it's called print. So P, we want to print assembly. So PA question mark. Okay, PA add, no. PD for print disassembly. And we want a PD. Okay, now it prints a lot more. So we want P disassemble PD length of 1. Cool. Okay, so here we have the jump not equal. Now we want to write something. So write question mark, write opcode, write assembly, write an opcode, jump equal, and then the address, fail to write. Okay. Modify opcode. O, and let's turn this into a jump equal. Oh, okay, it doesn't know JE, so maybe JZ. Did we do anything? Oh, I'm an idiot. My bad. I had to make sure that the file is in writable mode. That's why the writes failed earlier, and now it works. But, you know, small pet peeve. I tried to assemble JE, but that was not allowed. JZ was allowed, but the disassembly then shows JE again. Right there. Never change. Never change, please. Okay, so let's check. Did we already like write to the file? I assume so. So let's just exit and execute the license file. So we patched it with radare2. That joke was good.